Welcome, learner, to a deep dive that pulls back the curtain on the silent, constant changes happening all around us.
It really is amazing when you stop and think about it.
Today, we're tackling a fantastic set of sources, all detailing the very language of matter, chemical reactions and equations.
It's so easy to just walk through the world and see things as, well, stable, fixed.
Right. Stillness.
But if you could zoom right down to the atomic level, oh, it's constant motion. Atoms breaking bonds, forming completely new ones,
We are absolutely surrounded by chemistry.
all the time. And often it's happening so slowly, or maybe so subtly, we just don't notice these huge transformations taking place, right under our noses.
And that's really the core mystery we want to dig into today, isn't it? The mystery of the mundane.
Exactly.
Our sources kick things off with some really great everyday questions, like think about milk, fresh milk you bought yesterday. What happens when it sours in the summer heat?
It's definitely not milk anymore, is it?
Not at all. Something totally new. Or think about an iron pan, maybe one you left outside accidentally. Shiny 1 minute.
And the next, covered in that flaky reddish-brown stuff. Rust.
Or even more basic, think about us, our own bodies. The food digesting, the simple act of breathing in and out.
In every single one of those cases, the souring, the rusting, digestion, breathing, the actual nature, the identity of what you started with, it's fundamentally changed, morphed,
And when that identity changes, well, that's it. A chemical change has occurred.
which means a chemical reaction has taken place. Simple as that.
It's like this invisible engine driving everything from, food spoiling in the fridge to making cement for buildings.
Absolutely. So our mission today, it's a bit ambitious maybe.
Let's go for it.
Okay. We want to uncover the key signs, the visible clues that tell us a reaction has happened.
The indicators.
Then we need to get a handle on the language chemists use this concise, really elegant way of describing reactions using equations.
Makes sense.
And finally, we'll explore the main sort of family types of these chemical changes. The goal is that by the end of this, you'll feel instantly well-informed about the chemistry that shapes your daily life.
Sounds like a plan. Let's dive in. Where do we start? With the witnesses.
Right. If the actual atomic shuffling is invisible, the big question is, how do we know? How do we as observers see the evidence?
We need clues.
Exactly. We rely completely on the physical clues, the undeniable witnesses that tell us, yes, a reaction happened and something new got made.
Okay, so the sources start with a bang, almost literally. Activity 1.1, the magnesium ribbon.
Ah, yes.
A classic. But before you even get to the exciting part, it says you have to clean it first. With sandpaper. Why bother with that?
That's a really sharp observation. You see, magnesium is quite reactive. When it just sits in the air, it forms this thin, kind of dull layer of magnesium oxide on the surface.
Ah, like a protective coating.
Sort of, yeah. And that layer actually slows down or even stops the reaction we want to see. So you sand it off to get to the clean, reactive magnesium underneath. Makes the experiment much more dramatic.
And dramatic it is. You hold that clean ribbon with tongs, bring it to a flame, and wow!
It's quite the spectacle.
It's like a little chemical firework. Burns with this dazzling white flame, super intense, and the whole ribbon just turns into this fine white powder.
What you're seeing there is the magnesium metal reacting, combining really with oxygen gas from the air.
Okay.
And it forms a totally new compound, magnesium oxide, MgO, that white powder.
So right there, we see two big clues, don't we?
Definitely. First, a change in state. You go from a solid metal ribbon to a powdery ash.
And second,
Well, that dazzling light is energy being released. Light and heat, that's another major indicator.
and the source even warns you, right? Keep it away from your eyes.
Yes, that tells you something about the intensity. It's a rapid, very energetic reaction, not just a gentle warming.
Okay, so intense light and heat is one clue. What else? Activity 1.3 gives us a couple more practical signs.
It does. These are maybe a bit more subtle. This is where you take some zinc granules.
Little bits of zinc metal.
Right, and you put them in a flask and add some dilute acid, like hydrochloric acid or sulfuric acid.
And what's the first thing you'd notice? Visually.
Immediately, you'd see bubbles. Lots of bubbles forming all around the zinc granules. That's the evolution of a gas.
A new gas is being made.
Precisely. It wasn't there before, so its appearance strongly suggests a chemical reaction is producing it.
But then the source says, go on, touch the flask, be brave.
Huh. Yes, and if you do,
You feel something.
you do, you'll notice a definite change in temperature. In this particular case, the flask gets noticeably warmer. Energy is being released.
Ah, so heat release again, like the magnesium, but maybe less dramatic.
Exactly. It's another key indicator.
Mm.
And we'll talk later about how we classify reactions based on whether they release heat or absorb it.
Okay, so we've got dazzling light, gas bubbles, temperature changes. What if everything stays liquid? Activity 1.2 seems to focus on color.
Right. This one is visually very striking. You take two clear, colorless solutions,
Yeah.
lead nitrate solution and potassium iodide solution.
Both look just like water initially.
Correct. But the moment you mix them, boom,
What happens?
instant drama. The mixture immediately turns this vibrant, opaque yellow, a massive change in color.
Wow, why?
It's because a new substance is formed, lead iodide. And this lead iodide is insoluble in water. It doesn't dissolve.
So it makes the liquid cloudy and yellow.
Exactly. We call that insoluble solid a precipitate, and its sudden appearance is a dead giveaway that the atoms have rearranged. A reaction occurred.
That's fantastic. Instant chemical proof. Okay, so let's pull those 4 key witnesses together for the learner. What are the main things to look for?
The 4 big ones are, first, a change in state, like solid to powder or liquid to gas. Second, a change in color.
Got it.
Third, the evolution of a gas seeing bubbles where there were none before. And fourth, a noticeable change in temperature, either getting hotter or colder.
So if you see any one of those, you can be pretty sure a chemical reaction has happened.
That's the essence of it. Those physical changes are our window into the invisible world of atoms breaking and making bonds. It's the proof that the identity of the substances has truly changed.
Amazing how these big visible clues tell us about tiny atomic rearrangements. Okay, we know what to look for now. Let's tackle the language chemists use to describe all that.
Exactly. Seeing it as one thing, describing it efficiently is another. If we had to write out a long sentence every time, like zinc granules react with dilute sulfuric acid to produce hydrogen gas and zinc sulfate solution releasing heat, well, it gets cumbersome.
Yeah, we'd be here all day. We need shorthand.
And the first step towards that shorthand is the word equation. Think of it as a bridge between the full description and the super condensed chemical symbols.
How does that work?
It's got a really clear logical structure. On the left-hand side of the LHS, you list the starting materials, the reactants.
The things that react.
Right, connected by a plus sign if there's more than one. Then there's an arrow pointing to the right-hand side, the RHS.
And that's where the new stuff goes.
That's where the products go, the new substances formed by the reaction. The arrow shows the direction of change from reactants to products.
So for that magnesium example, it would be magnesium plus oxygen, magnesium oxide.
Perfect. Simple, clear, tells the basic story.
But chemists like things even shorter, right? That's where the formulae come in.
That's the ultimate goal. Using the chemical formulae gives us the true power of the chemical equation.
So instead of words, we use symbols. Mg plus O euro, MgO.
Exactly. Looks neat, right?
Gotcha.
But hang on. We immediately run into a fundamental problem, a really big one.
Uh-oh. What's that?
Count the atoms. On the left, in O euro, how many oxygen atoms do we have?
2.
And on the right, in MgO.
Just 1. They don't match.
They don't. And this brings us straight to maybe the most important rule in all of chemistry, the law of conservation of mass.
Ah, I remember this. Mass can't be created or destroyed.
Got it. In a normal chemical reaction, atoms don't just vanish into thin air, and new ones don't magically appear out of nowhere, they just rearrange.
So if the atoms just rearrange, the total mass you start with must be exactly the same as the total mass you end up with.
Precisely. And if the total mass is the same, then the number of atoms of each specific element has to be the same on both sides of that arrow, before and after the reaction. No exceptions.
Okay, so our simple Mg plus O euro equation is incomplete.
It is. We call it a skeletal chemical equation. It shows who the players are, the reactants and products,
Yeah.
but because the atom count isn't equal, it doesn't respect the law of conservation of mass. It's unbalanced.
It needs balancing.
It must be balanced to be scientifically correct.
And how do we do that? Especially for reactions that look more complicated. The sources mention a hidden trial method.
Yes, it sounds a bit random, but there's a logic to it. Let's take that complex example from the source. Iron reacting with steam. The skeletal equation is text 4, text 2, text O4 plus text 2.
Okay, that looks a bit intimidating. Iron plus water gives iron oxide and hydrogen gas. Where do we start?
Step 1 is crucial, mentally.
Mm-hmm.
Draw boxes around each formula. Box text 4 plus box text 2 text 4 plus box text H2.
Why the boxes?
It's a reminder. You cannot change anything inside the box. You can't change H euro to H euro to make the oxygens balance. That changes the substance. You can only put whole numbers, coefficients, in front of the boxes.
Okay, so we can have multiple water molecules, but each one is still HO. Got it.
Now, the trick, the strategy, is not to start balancing randomly. Pick the compound with the most atoms in it.
In our example, that would be a thio. It has 3 irons and 4 oxygens, so 7 atoms total.
Good. Now, within that compound, pick the element with the most atoms.
That would be oxygen. There are 4 oxygen atoms in thio.
Perfect. So we start by balancing oxygen. We have 4 O atoms on the right, whereas oxygen on the left.
Only an HRO, and it only has 1 oxygen atom per molecule.
So to get 4 oxygen atoms on the left, what coefficient do we need in front of HO?
We need 4 water molecules, so a 4.
Excellent. Let's rewrite it. Box 3 text to phi, text O4 plus box to O4. Now, oxygen is balanced, but what did putting that 4 in front of water do to hydrogen?
Ah, right. Now we have 4 times H here, so 4 by 2 is 8 hydrogen atoms on the left.
Okay, look at the right side. How many hydrogens do we have?
Just H here, so only 2.
How do we get 8 hydrogens on the right?
We need 4 HRO molecules. So put a 4 in front of the HO.
You got it. Now we have dox text 2 text right arrow box 3 text O4 plus 4 box text O4. Let's check. Oxygen is 4 on both sides. Hydrogen is 8 on both sides. What's left?
Just the iron, P. On the right, in FeSO, there are 3 iron atoms.
And on the left?
Just 1 Fe atom so far.
So the final step.
Put a 3 up in front of the Fe on the left.
Let's write the whole thing out. $3 text free text O right, or text 3 text O4 plus 4 text O.
Oh.
Now quickly count everything. 3Fe left, 3Fe right, 8H left, 8H right, 4O left, 4O right.
It works. It's balanced. It feels like solving a puzzle.
It really is a logical puzzle, all based on that conservation law. But wait, we can make this equation even more informative.
How so?
By adding context. We need to know the state these substances are in. Are they solid, liquid, gas, dissolved in water?
The state symbols, like S for solid, L for liquid,
G for gas, and AQ for aqueous, meaning dissolved in water. These little symbols add crucial detail.
So for our iron and steam reaction, iron is a solid, right?
FES, and we said it reacts with steam, not liquid water.
So water should be HE. That's important.
Very important. The product euros is a solid, so S, and the hydrogen produced is a gas, HG.
Okay, so the fully informative equation is $3 text totals plus 3 text F2 text 2 plus 4 text right text totals plus 4 text total. That tells a much richer story.
It does. And sometimes you need even more information. Specific conditions might be required for the reaction to even happen.
Like what?
Things like temperature, pressure, or maybe a catalyst, a substance that speeds up the reaction without being used up itself.
And where those go?
Usually written right above or below the arrow in the equation. Think about photosynthesis in plants.
Need sunlight and chlorophyll.
Exactly. So you'd write sunlight and chlorophyll above and below the arrow in the equation for photosynthesis. Or making methanol that needs incredibly high pressure, 340 atmospheres. You have to write 340 at M over the arrow.
So the equation becomes like a recipe. It tells you not just what reacts and what forms, but how to make it happen.
That's a great way to put it. A complete, balanced chemical equation with state symbols and conditions is a precise recipe for chemical change.
Okay, we've got the language down. Now let's talk about the different types of reactions. It's not just one big jumble, is it? They fall into categories.
That's right. At their heart, all reactions involve breaking old chemical bonds and making new ones. But we can group them based on the pattern of what happens to the reactants. It helps us predict outcomes and understand chemistry better.
Like families of reactions. Where should we start?
Let's start with the simplest idea, putting things together. Hashtag tag 3.1 combination and exothermic reactions.
Okay, the name sounds straightforward. Combination reactions.
It is. This is where 2 or more substances could be elements, could be compounds, combined to form one single new product. A plus B, AB, basically.
And the sources give a really common example. Whitewashing walls. Activity 1.4.
Ah, yes, a very practical one. You start with quicklime, which is calcium oxide, CaO. It's a white solid.
And you mix it with water, HO.
And it reacts quite vigorously. They combine to form slaked lime, which is calcium hydroxide, CaO.
Plus HOO, a single product from 2 reactants. Combination.
Exactly. But there's something else really important happening here, something you can feel.
The source says if you touch the container, it gets hot.
Very hot, actually. It releases a large amount of heat. You need to be careful.
So this reaction doesn't just make a new substance, it also releases energy.
Correct. And that makes it an exothermic reaction. Exo meaning out, thermic meaning heat. Any reaction that releases energy, usually is heat, into its surroundings is exothermic.
Combination reactions are often exothermic then.
Very often, yes. Forming new bonds usually releases energy.
And the whitewashing story doesn't end there, does it? The slaked lime solution goes on the walls.
Right, you paint it on. But it's not instantly shiny white. That takes a couple of days.
Why? What's happening?
The slaked lime, castles, slowly reacts with carbon dioxide, casho, that's naturally present in the air.
Ah, another reaction.
Yes. And this reaction forms a thin, hard, shiny layer of calcium carbonate, CaCO, on the wall, plus some water, which evaporates.
Now, wait, isn't that the chemical formula for marble?
It is indeed. So when you whitewash, you're essentially creating a very thin, synthetic layer of marble on your walls through these combination reactions. Pretty neat, yeah?
That's amazing. And exothermic reactions aren't just for whitewashing. Burning natural gas, CH, for heating.
Classic exothermic combination. Methane plus oxygen gives carbon dioxide and water and lots of heat.
And what about us? Respiration.
Absolutely vital. That's also exothermic. Glucose from our food combines with oxygen in our cells.
CH euro plus oro.
Gives chiro and, crucially, releases the energy that keeps us alive and warm. It's a controlled, slow exothermic combination happening inside us constantly. Hashtag 3.2 decomposition and endothermic reactions.
Okay, if combination is putting things together, the opposite must be breaking things down.
Exactly. That's decomposition reactions. Here, a single reactant breaks down into two or more simpler products. AB, A plus B. It's the reverse pattern.
Makes sense. If forming bonds releases energy, exothermic, does breaking bonds require energy?
Generally, yes. To break the bonds holding the starting compound together, you usually need to put energy in.
So decomposition reactions need an energy source.
They do. They require energy in the form of heat, light, or electricity to happen. And because they absorb energy from their surroundings, we call them endothermic reactions. Endo meaning in.
Okay, so decomposition is usually endothermic. What are some examples? The sources mention different energy types triggering it. Let's start with heat thermal decomposition.
Right. Activity 1.5 describes heating ferrous sulfate crystals. They start off green, FeSO.
What happens when you heat them?
First, they lose some water, change color. But if you keep heating strongly, the FeSO itself decomposes. It breaks down into iron oxide, a reddish-brown solid, into two gases, sulfur dioxide, SO, aero, and sulfur trioxide.
And you'd know because...
You'd smell it. Those sulfur gases have a very characteristic pungent smell, like burning sulfur. You're observing the breakdown products.
Another big industrial example mentioned is heating limestone. Cateau.
Yes, we saw CaCO forming during whitewashing. If you heat it very strongly, thermal decomposition, it breaks back down into quicklime, CaO, and carbon dioxide.
CO.
Yep.
Ooh, that's stuff used to make cement, right?
A key ingredient, yes. So this decomposition reaction is hugely important industrially. Activity 1.6 also shows heating lead nitrate, another white solid.
What happens there?
It decomposes to give lead oxide, oxygen gas, and distinctive brown fumes. Those brown fumes are nitrogen dioxide gas and O-aero, another clear sign of decomposition driven by heat.
Okay, so heat can break things down. What about light, photodecomposition?
Activity 1.8 uses silver chloride, AgCl, to white solid.
What does light do to it?
If you just leave it out in the sunlight, it slowly turns gray. The light energy is enough to break the AgCl down into solid silver metal, Ag, which looks gray or black in fine particles, and chlorine gas, Cl, which escapes.
Silver metal, huh? Does this have any practical use?
Oh, historically massive. The source points out this reaction, and a similar one with silver bromide, AgBr, is the entire basis for traditional black and white photography.
Really? How?
The photographic film was coated with these silver compounds. Where light hit the film, the silver compound decomposed, leaving tiny black silver particles. Where no light hit, it stayed white. That created the negative image, light energy causing a chemical change.
Wow. Okay, so heat, light. What's the third energy source for decomposition?
Electricity. We call this electrolysis, electricity. Electrolysis meaning splitting. Activity 1.7 is the classic electrolysis of water.
You pass electric current through water using electrodes.
Yes, usually graphite electrodes, and you need to add a tiny bit of acid to help the water conduct electricity. The electric energy forces the water molecules to break apart.
Into what?
Into their constituent elements. Hydrogen gas, H, and oxygen gas.
Yeah.
You can collect these gases separately.
And the sources mention a really cool observation here, the aha moment. Something about the amounts of gas collected.
That's right. If you collect the gases in inverted test tubes over the electrodes, you find you collect exactly double the volume of hydrogen gas compared to oxygen gas.
Double the hydrogen. Why?
Think about the formula for water, HO. For every one oxygen atom, there are 2 hydrogen atoms.
Ah, so when it splits, you get 2 hydrogen molecules for every 1 oxygen molecule. The 2.1 ratio in the formula dictates the 2.1 volume ratio of the gases produced.
Precisely. It's a beautiful, visible confirmation of the chemical formula driven by the input of electrical energy. Endothermic decomposition. Hashtag 3.3 displacement reactions.
Okay, moving on. We've done combining and splitting. What about reactions where things get swapped around, like displacement reactions?
This is where reactivity comes into play. In a single displacement reaction, a more reactive element essentially kicks out or displaces a less reactive element from its compound. Think of it as a chemical swap based on strength.
A more reactive element bullies its way in.
Kind of, yeah. Activity 1.9 shows this perfectly. You take a clean iron nail,
Just a regular iron nail.
and you dip it into a solution of copper sulfate, CuSO. Now, copper sulfate solution has a really distinct bright blue color.
Okay, iron nail in blue liquid. What happens?
You leave it for maybe 10-20 minutes. When you take the nail out, you see 2 clear changes.
What are they?
First, the part of the iron nail that was in the solution is now coated with a brownish layer.
Brown. What's that?
That's pure copper metal,
Mm.
CuLO, that has been kicked out of the solution and deposited onto the nail.
Whoa, and the second change?
The blue color of the copper sulfate solution has faded quite noticeably. It might even look slightly greenish
Why does it fade?
because the iron Fe is more reactive than the copper CO. The iron atoms go into the solution, displacing the copper ions. They form iron sulfate solution, BaSO, which is pale green. So the blue copper sulfate is used up, replaced by greenish iron sulfate, making the overall blue color fade.
So the iron pushed the copper out of the compound and took its place. Fe plus CuSO, FeSOA plus Q.
That's the reaction. Iron displaces copper. The sources also mention that other metals like zinc, Zn, and lead, Pb, can also displace copper from copper sulfate solution.
Meaning zinc and lead are also more reactive than copper.
Correct. There's a whole hierarchy, a reactivity series of metals, that predicts which element can displace another. It's like a chemical pecking order. Hashtag 3.4 double displacement reactions.
Okay, so that was single displacement, one element kicking another out. What about double displacement? Does that mean 2 things get swapped?
Exactly. In these reactions, you typically have 2 ionic compounds dissolved in water, and they essentially swap partners. There's an exchange of ions between the 2 reactants. AB plus CD, AD plus CB.
An ion exchange. Activity 1.2 gives an example.
Yes, mixing sodium sulfate solution with barium chloride solution, BaClO. Both are clear, colorless solutions.
Okay, 2 clear liquids again. What happens when they mix?
Immediately, you see a white substance forming in the mixture. It makes the whole thing look milky or cloudy.
Another precipitate, like the yellow one we saw earlier.
Precisely. This white substance is barium sulfate. It forms because the barium ions from barium chloride combine with the sulfate ions from sodium sulfate, and BaSO is insoluble in water, so it precipitates out.
So the Bach and Nia swapped partners with the SOO and Cla.
That's right. The sodium ions, Ni, combine with the chloride ions, thachlorate, to form sodium chloride, NaCl, common salt. But NDL is soluble in water, so it just stays dissolved. You don't see it forming.
So the reaction is NiSO plus Baclo plus 2 NaCl's. The key observation is the solid BSO forming.
Correct. And because a precipitate is formed, we also call this specific type of double displacement reaction a precipitation reaction. Any reaction that produces an insoluble solid precipitate falls under this definition. It's all about that ion exchange leading to an insoluble product.
All right, we've covered combining, splitting, and swapping. Now we get to a really fundamental pair of processes that underlie so many reactions: oxidation and reduction.
Ah, yes, the redox duo. You almost never have one without the other. They are 2 sides of the same coin.
So how do we define them? The sources start with oxygen and hydrogen, which seems helpful.
It's a good starting point.
Yeah.
Traditionally, oxidation was defined as the gain of oxygen by a substance, or alternatively, the loss of hydrogen.
Okay, gain oxygen or lose hydrogen oxidized. What about reduction?
Reduction is the opposite. It's defined as the loss of oxygen or the gain of hydrogen.
Lose oxygen or gain hydrogen reduced. Got it. And you said they happen together.
Always in what we call redox reactions.
Mhm.
If one substance loses oxygen, gets reduced. Another substance must gain that oxygen, get oxidized. The oxygen just moves from one place to another.
Like a transfer.
Exactly. Or hydrogen gets transferred. Something is always oxidized and something else is always reduced simultaneously.
The copper powder demonstration, activity 1.11, seems to show this really well both ways.
It does. You start with copper powder, which is brownish.
Yeah.
It's the Leonish in R. You heat it in a dish open to the air. The surface of the copper turns black. It reacts with oxygen from the air.
So the copper gains oxygen.
Yes, it forms black copper 2 oxide, CuO. Since the copper gained oxygen, we say the copper has been oxidized. Q plus OVO unbalanced.
Okay, copper gets oxidized, but then the experiment reverses it. You pass hydrogen gas, H, over the hot black CuO.
Right, and when you do that, the black coating turns back into brownish copper metal.
Whoa, so the CuO lost its oxygen.
It did. Since CuO lost oxygen, we say it has been reduced back to Q.
But where did the oxygen go?
Look at the other reactant, hydrogen gas, H. The hydrogen takes that oxygen from the CuO and forms water, HO.
Ah, so the hydrogen gained oxygen.
Meaning the hydrogen was oxidized. So in this second step, CuO plus HCO plus HO, the CuO is reduced and the H is oxidized. See, they happen together. One loses oxygen, the other gains it.
That makes sense. Reduction and oxidation are linked. The source gives other examples too, like zinc oxide reacting with carbon, ZNO plus C, ZO plus CO.
Perfect example. The zinc oxide, ZNO, loses oxygen, so it's reduced to zinc, Zn. The carbon C gains that oxygen, so it's oxidized to carbon monoxide, CO. Redox again.
It's a really powerful concept, but oxidation isn't always a good thing, is it? The sources talk about harmful effects in daily life.
Oh, absolutely not always good. Uncontrolled oxidation causes major problems. The first big one is corrosion.
Rusting, basically.
Rusting of iron is the most common example, yes, but corrosion is the general term for when a metal is attacked, usually oxidized, by substances in its environment like moisture, air, acids.
So that reddish-brown powder on rusted iron is iron oxide, formed by oxidation.
Exactly. Other examples are the black tarnish that forms on silver objects, that's silver sulfide, formed by a reaction involving sulfur compounds in the air, often considered a type of corrosion or oxidation. Or the green coating, patina, you see on old copper roofs or statues. That's also corrosion products forming.
And the sources emphasize that this isn't just a cosmetic issue. Corrosion, especially of iron, it's a huge problem.
It's an enormous economic problem. Think about it. Bridges, ships, car bodies, pipelines, reinforced concrete structures, they all rely on iron and steel.
And they all rust.
They all rust. This constant degradation costs billions upon billions worldwide every year in damage, repairs, and replacements. It's a massive, ongoing battle against unwanted oxidation. Understanding redox is step one in trying to prevent it.
Wow. Okay, what's the second big unwanted oxidation effect? Something that hits us more personally?
Rancidity. This hits us right in the kitchen.
Rancidity, what's that?
It's specifically the oxidation of the fats and oils present in food. When foods containing fats or oils are exposed to air for too long, the fats react with oxygen.
They get oxidized.
Yes, and this oxidation produces new chemicals that have unpleasant smells and tastes. Basically, the food goes bad, it becomes rancid.
Ugh, nobody wants rancid food. So how do we fight this kind of oxidation?
Well, knowing its oxidation gives us clues. Food manufacturers often add substances called antioxidants to foods that contain fats and oils.
Antioxidants, what do they do?
They're chemicals that get oxidized more easily than the fats themselves. So the oxygen reacts with the antioxidant first, essentially sacrificing itself to protect the fats and delay rancidity.
Clever. What about simple things we can do at home?
The most basic thing is limiting oxygen exposure. Keeping fatty foods in airtight containers slows down the oxidation process simply because there's less oxygen available to react.
Makes sense. Less oxygen, less reaction.
And then there's the chip strategy. You know how bags of potato chips seem puffed up with air?
Yeah, mostly air sometimes feels like.
Well, it's usually not air. Manufacturers flush those bags with nitrogen gas before sealing them.
Nitrogen. Why nitrogen?
Nitrogen is very unreactive. By filling the bag with nitrogen, they push out most of the oxygen. Without oxygen, the oils in the chips can't get oxidized easily, so they don't go rancid. The chips stay fresh and crispy much longer.
Huh. So that puffiness is actually protecting the chips from oxidation. That's really smart. Apply chemistry in a snack bag.
Isn't it? Understanding redox helps keep our snacks tasty. Hashtag #OTRO synthesis and final thought.
We really have covered a lot of ground today, learner. We started just by noticing everyday things, milk souring, that amazing flash from magnesium burning, walls getting shiny after whitewashing.
And we realized that all these seemingly different events are actually governed by predictable, well-understood chemical changes. They all follow rules.
We learned the language needed to describe these changes accurately, how to write and balance chemical equations, making sure we always respect that fundamental law of conservation of mass.
hmm And we saw how reactions fall into families based on what they do. Combination, decomposition, displacement, double displacement, and also based on how energy flows exothermic releasing heat, endothermic absorbing it.
And finally, we connected that core concept of oxidation and reduction, the simple gain or loss of oxygen or hydrogen, to huge real-world issues, both destructive things like
A
corrosion
massive global problem.
and everyday annoyances like food going rancid. Plus, the clever ways we fight back using chemistry, like antioxidants or nitrogen flushing.
It really shows how chemistry is just woven into everything, doesn't it? Visible or invisible, it's always happening.
It really does. Now, we mentioned earlier that photodecomposition, using light energy to break down silver compounds, was key for old-school black and white photography.
Right, a classic technology relying on a specific energy input, light, to drive a chemical change.
So here's a final thought to leave you with. What other, perhaps seemingly simple, foundational chemical processes, maybe ones that also need a very specific energy input like heat or light or electricity, what other reactions like that might still form the absolutely essential basis of some very advanced cutting-edge technologies we rely on today?
That's a great question. What old chemistry powers new tech? Something for you to ponder and explore until our next deep dive.